Okay, so let us start. We defined resolution of identity, we saw an example and we wrote down a proposition which develops the integration with respect to a resolution of identity, right. For any continuous function on minus r to r, that is the support of the resolution of identity, it is possible to form these Riemann sums using the resolution of identity and then prove that their limit exists. Okay. So, consider it to be the integral of your continuous function with respect to the resolution of identity. So, let us try to prove that. Okay. So, let us start. So, let us quickly look at the statement again. Let E t be a resolution of identity supported in minus r to r. I take a continuous function and then form these Riemann sums, right, phi n g equal to summation j equal to minus 2 to the n r to 2 to the n r. So, minus r to r is divided into intervals of length 1 by 2 to the n. Now, those are the Riemann sums and the Riemann sums converge in the operator norm to a bounded operator, right, we denote it by phi of g. Okay. So, we will change that notation later and it has these 4 properties. Okay. So, the 4 properties are, one is it is linear, which is trivial, and it preserves the star operation, that is also trivial to see. A third one is that operator norm of phi g is less than or equal to the supremum norm of g and it is multiplicative, it is an algebra homomorphism. So, we start with the proof now. Okay. So, proof of the proposition. Okay. So, this is going to be just like the proof that a continuous function's Riemann integral exists, right. So, essentially the same proof, except that we are dealing with projections and things like that, bounded operators. So, there are certain things one has to be very careful about. Okay. So, we first show that the limit exists. Okay. Everything else will follow once we show the same properties for the sequence phi n, okay, because all those properties will carry forward to the limit as well, right. So, note that, so in this we need to recall the result we proved about projections in the last class, right. So, or the class before that. So, let me recall that if I had projections, so p q projections, right, p less than or equal to q, then range of p was contained in range of q, right. Q minus p was the projection onto whatever is remaining in range of q, right, which is orthogonal to range of p. So, that is range p, the orthogonal complement, whatever is inside range q, right. So, intersection range q, okay, and p q equal to q p, right. So, we proved this result about projections in the 2 classes before, I guess. So, we will use all this. So, all the E sub t's are projections and we have p less than or equal to q, right. So, the E sub t is less than or equal to E sub s if s is greater than t, right. So, all these results can be used for those projections and that is what we will do. Okay. So, if let us take T 1 less than S 1 less than T less than S. Okay. So, yeah, let us write S there. So, I take 4 points, the middle ones S 1 and T could also be equal, but for the time being let us take them strictly S 1 strictly less than T. Then from whatever we have proved from the earlier result about projections, we have well all these results we have, right, because well we have, because, so let me write because T 1 is less than S 1 less than T less than S, we have E T 1 less than or equal to E S 1, right. These are self adjoint operators, and so E T 1 less than or equal to E S 1, meaning E S 1 minus E T 1 is a positive operator, right, less than or equal to E sub T less than or equal to E sub S, right. We have this, and we can apply the result for projections. We have range of, so I will write down and then explain E S minus E T. Okay. So, I am taking the first two, right, E S minus E T, that is going to be orthogonal to range of E S 1 minus E T 1. Okay. We'll write it, we'll see the proof immediately using whatever results we have on projections. Okay. So, let us let's keep the picture in mind. So, this is T 1, this is S 1, this is T, this is S. As I said, the middle ones could be the same, okay, but let's stick to this case first and then see what happens. What do we know about projections P less than or equal to Q? Well, Q minus P, we are looking at Q minus P, right. We are looking at E S minus E T and E S 1 minus E T 1, right. So, that is like P minus Q, we know something about them, right. So, let me write down the results and then try to well, the first result. So, the ranges are contained in the bigger range of the bigger projection. So, we start with that. So, range of E T 1, right, that will be contained in range of E S 1, right, because T 1 is less than or equal to S 1, and this is contained in range of E T contained in range of E S, right. So, range of E S is the biggest among these, right, and each of them. So, you have the orthogonal complement of each of them in the immediately the first one, right. So, that is the Q minus P is the projection to that part, right. So, the when I take the difference of two things E S and E T, E S minus E T is going to be a projection onto whatever is remaining in the range of E S, but orthogonal to range of the smaller projection, right, that is what this is. So, let us write down that in picture, so that it is much easier, because if I write it in words it will look very messy and it will not be very clear at all. So, let us say this is range of, so this is range of E sub S, that is the biggest one, right, this guy. Okay. Now, look at the first one. So, T, range of E T. Okay. So, range of E T, so let us say up to here, this is range of E T, right. Range of E T is contained in range of E S. So, it is a subspace, closed subspace of range of E S. Okay. What is here? What is remaining? What is remaining is the range of the difference E S minus E T, right, because what is remaining is the orthogonal complement of range of E T, but inside range of E S, right. So, that is this guy. Okay. So, whatever is remaining there is the range of, so let me write down this is range of E S minus E T. Okay. The extra box there, which is orthogonal to range of E T, is the range of E S minus E T. Okay. Now, we go here, range of E S 1 is contained in range of E T. So, let us say this one. So, this is range of E S 1, E sub S 1, right, that is fine, because that is contained in range of E sub T. Okay. And well, here I have range of E T 1, which is the smallest one. So, I will put this as range of E T 1. So, let me write it here, range E T 1. Okay. So, inside range of E S 1, whatever is the orthogonal complement of range of E T1, sorry not T, T1 would be the range of the difference of those projections, right. So, this portion is the range of E S1 minus E T1. Okay. So, obviously, this subspace and this subspace are orthogonal to each other, right, because this subspace whatever is here is orthogonal to whatever is on the left hand side, right. So, this is obviously true now, right, from the picture it is very clear that it is true. Now, you can see that the same holds even if S1 and T were same. Okay. So, note that the same holds if S1 equal to T. So, what does it mean to say S1 equal to T? That is the middle two things are same, right. So, you will have this which is range of S, then I have S1 equal to T here, right, and something here, right. So, the same proof says that whatever is here would be, whatever is on this side would be orthogonal to whatever is here, right. So, range of E s minus E t will be orthogonal to range of E t minus E 1. So, in other words, it is easier to say in this form, if I take two disjoint intervals, the intervals, right, then the range of the difference of the projections at the end points will be orthogonal to each other. Okay. So, that is a better way of saying. In other words, if I have two intervals A and B, the endpoints may agree, but even then you will have the right. So, okay, maybe it is better to write it like this. So, if A less than B less than equal to C less than D, okay, then range of E d minus E c, right, is orthogonal to range of E b minus E a. Okay. That is what we have just proved, right. I just drew the picture to tell you, to justify that this is true. You can write down it in words, but it is going to be slightly messy, that is all. You need to know where these spaces are sitting inside, right, that is all you need to know. Okay. Once this orthogonality is established, you can look at the Riemann sum very carefully. So, recall that. So, I want to write down the Riemann sum again and see how it looks like, because I want to say that it converges in the norm, right. So, hence recall that phi n g was you look at the interval minus r to r, you decompose that into intervals of length 1 by 2 to the n, right, that is the nth level. So, I have j going from minus 2 to the n r to 2 to the n r, okay, and g j by 2 to the n, e j by 2 to the n minus e j minus 1 by 2 to the n. Okay. So, yeah, I should have explained this once. The left end point of the summation or the bottom end point of the summation is j equal to minus 2 to the n r, and I have something here j minus 1, right. J minus 1 will take me by 2 to the n will take me outside minus r. So, then it is already 0. Okay. So, remember the resolution of identity is supported in minus r to r, right. So, E when j is minus 2 to the n r, I have minus 2 to the n r minus 1 by 2 to the n, right. So, this is E minus r minus 1 by 2 to the n So, minus r minus by 2 to the n, one is less than minus r. Okay. So, this is 0. So, at the end point one projection is 0. Okay. Remember that. Okay. So, phi n g is this, right. Now, I want to show that phi n g converges to something in the operator norm, right. Alright. So, let us first of all act it on a vector x and see what happens. Also recall that these are intervals j by 2 to the j minus 1 by 2 to the n to j by 2 to the n, right. These are disjoint intervals, right. The endpoint may coincide, but we have already taken care of that, right. So, the ranges of the projections which appear here E j by 2 to the n minus E j minus 1 by 2 to the n, the ranges of them are orthogonal to each other. Okay. So, let us act it on a vector x and see what happens. So, if x is a vector in the Hilbert space H, compute. So, let us compute phi n g x norm square. Okay. So, what is this? So, let me write down one step, j equal to minus 2 to the n r 2 to the n r g of j 2 to the n, and then these projections, right. So, the projection acting on x. So, E j by 2 to the n minus E j minus 1 by 2 to the n acting on the vector x. Okay. So, these vectors, because the range of E j by 2 to the n and j minus 1. So, let me write that separately. Note that the range of E j by 2 to the n minus E j minus 1 by 2 to the n and range of E, let us say k by 2 to the n minus E k minus 1 by 2 to the n are orthogonal if j is not equal to k. Right. If j is not equal to k, these two intervals are disjoint. At the most they can agree at one endpoint, but then we have already seen that range of two such intervals, right, the projections coming from two such intervals would be orthogonal to each other. Okay. So, because of that, if I look at these vectors, so these are orthogonal to each other, orthogonal vectors, right, because these are in the range of the corresponding projections and these ranges are orthogonal. In other words, E j by 2 to the n minus E j minus 1 by 2 to the n acting on x is orthogonal to E k by 2 to the n minus E k minus 1 by 2 to the n acting on x, right. So, if you look at this more carefully, this is like summation some numbers, let us say a j, some vectors x j, where x j are orthogonal, right. So, if I take linear combination of vectors which are orthogonal, it is easy to compute the norm, right, norm square of that. So, let us do that. So, I am looking at the norm square of this. Since they are orthogonal to each other, I can write this as this is less than or equal to, well, what will happen, or let me write one more step so that this is clear. This is equal to summation, they are orthogonal to each other. So, minus 2 to the n r 2 to the n r, okay, modulus of g j by 2 to the n square, right, because the summation a j x j, if x j are orthogonal and I am taking the norm square, that is going to be summation mod a j square norm x j square, right, that is how it will look like. So, that is what I am going to write down, and norm E j by 2 to the n minus E j minus 1 by 2 to the n this operator acting on x norm square, right. That is how the norm is, which is less than or equal to. So, let us go to the next page. Okay. I take the supremum of G outside, right. So, supremum over J mod J G of J by 2 to the n, right. So, J will go only from minus 2 to the n r to 2 to the n r. Of course, you can bound it by the L infinity norm of G, right, the supremum norm of G, that is what we want finally, but let us keep this because we to prove that the limit exists we need to do a slightly more delicate estimate. So, I take the supremum of J G J by 2 to the n outside, where J runs from minus 2 to the n r to plus 2 to the n r, right. Whatever is remaining, so let us write down that again, J equal to minus 2 to the n r to 2 to the n r. Well, what is this? This is e to the e j by 2 to the n, right, the projection, minus e j minus 1 by 2 to the n x norm square, right. So, I have not done anything except using the orthogonality of ranges of these operators, right. Now, I can use it again, right, because these vectors are still orthogonal to each other. So, if I have use this, right. So, if I have x j is orthogonal, then the norm of sum of x j square is equal to norm sum of the norm squares, right, because they are orthogonal to each other. So, I have such a situation here, right. These vectors are orthogonal and I am summing up the norm square of them. So, it would be you sum up first and then take the norm square, right. So, this is equal to supremum over j mod G of j by 2 to the n. Well, I will take the norm square outside and then I can put the summation inside, right, that is what we are saying, minus 2 to the n r 2 to the n r e j by 2 to the n minus e j minus 1 by 2 to the n acting on x, and then you take the norm square, right, because all that we are using is they are orthogonal to each other, there is nothing else there. Okay. But now you have a telescoping sum, right, it is like n points will get cancelled, right. So, only the first one and the last one will remain. Okay. So, the inside part, since note that, so let me write this separately, note that summation j equal to minus 2 to the n r to 2 to the n r e j by 2 to the n minus e j minus 1 by 2 to the n acting on x, right. So, I want to sum up this, the middle terms will all get cancelled, the left end point, that is minus 2 to the n r will survive, and similarly the right end point j equal to 2 to the n r with, so that is just r, right. So, this is simply e the left end point and the so that is actually minus, right. So, maybe let me write the right end point first. So, that would be e r. So, 2 to the n r, right, j equal to 2 to the n r, I put e j by 2 to the n. So, I will get e 2 to the n r by 2 to the n, which is e r. Okay. Then the minus something, and in the next term that same thing will come with a plus sign and it all get cancelled, and only the last term the negative term will remain, right, whatever is coming with the minus, right. So, that is minus e j minus 1. So, that is minus 2 to the n r minus 1 by 2 to the n. Okay. But this one we already saw, that is actually equal to e to the minus r minus 1 by 2 to the n, and so it is 0, right. So, this is acting on x and this is equal to E r acting on x, but remember our resolution of identity is supported in minus r to r. So, this is simply x, right. So, I have proved that this is equal to supremum over j mod g of j by 2 to the n norm x square. Okay. All right. So, so let's just look at it again. What we have done is, if you look at phi n g x and look at the norm of this, then I have that phi n g x square is less than or equal to something about supreme, this is something which we will need later on also. So, keep that in mind, times norm x square. So, if the limit exists, then the same, so you can also bound it by the L infinity norm of g, so that there is no dependence on n, right. So, if the limit exists, then the limiting operator phi g will have the property that norm of phi g x is less than or equal to the L infinity norm of g times norm of x, right. So, if that is something we still have to prove, okay. We have not proved that the limit exists, we will prove that. So, if the limit exists, that is limit phi n g equal to phi g exists, then the above shows that phi g acting on the vector x, right, the norm square, well, the norm is less than or equal to L infinity norm of the function g, that is the supremum norm, times norm x, right, from here, because it is true for all phi n g's, and we have this, right. Consequently, that is same as saying, so that is, which is what one of the assertions was, the norm of the operator phi g is less than or equal to the L infinity norm. Okay. So, we still have to prove that the limit exists. Okay. So, maybe proving that the limit exists, we will do it in the next class, but let me just tell you what we will do. Okay. So, we look at phi. So, well, to show that the limit of phi n g as n goes to infinity exists, we need to show that the phi n g is a Cauchy sequence, right. So, fix g, look at phi n g as a sequence of operators. So, if that is Cauchy, then we know that it will have a limit, right, because these are operators, bounded operators, and bounded operators form a complete space, right. So, we will show that the sequence of operators phi n g is Cauchy in bounded operators on H, right. That is how, in fact, if you look at the way Riemann integral, existence of Riemann integral for continuous function, this is essentially what we will do. Okay. So, that is if let us say L is greater than n, the norm of phi L g minus phi n g, okay, right, that would be the way you prove that this is Cauchy, right. So, we want to show that this goes to 0 as L and n goes to infinity. Okay. So, that will prove that it is Cauchy, and hence the limit will exist. Once the limit exists, so we proved one of the properties, that is this property, if the limit exists, right. We still have to prove the other properties, okay, but those properties will follow once we show that phi n, at the nth Riemann sum has the same property, then, so in fact, we will see that the nth Riemann sum has the property that it is multiplicative, and when you take the the adjoint, it is same as taking the complex conjugate of the g and so on. Those things are actually not very difficult, and we can pass on to the limit once we prove it for all phi n g. So, that is what we will do in the next lecture. Okay. So, let us stop for the time being. We will complete the proof that the limit phi n g exists in the next class, and complete the proof of the extra properties that it is an algebra homomorphism and respects the star operation and well, the linear part is very trivial, right. So, and the fact that norm phi g is less than to L infinity norm or the supremum norm of g, all that will be proved by the end of the next class. Okay. So, let us stop for the time being.